Okay, so let's talk about the astrobiology of Kuiper Belt objects a little more. I'll focus again on Sharon specifically for this talk and the presence of oceans. And spoiler alert, it's more like past oceans, not current oceans, fortunately. But keep in mind that we know the Pluto-Charon system really well now compared to other Kuiper Belt objects, but these results, again, are applicable to many other places. And the reason why it's so interesting for astrobiology is that we know of about, say, a couple hundred objects larger than 200 kilometers in radius in the Kuiper Belt, and that outnumbers any other objects of the same size in our solar system. Presumably, it's the same thing in other solar systems as well, and so we might be looking at the most common type of solid worlds in the universe. And so if we can say something about the astrobiology, it's pretty cool. All right, so the Pluto-Charon system sits about 40 astronomical units from the sun. So for people who are not familiar with this, it's pretty far. So far that actually the surface of Charon is only about 40 Kelvin, as Brian mentioned. So Charon, I'll talk more about its structural properties, its interior, its evolution over time, and I think that's a good complement to the compositional information we just got from both Pluto and Charon. So Charon is about 600 kilometers in radius, and it has a density of about 1.6 grams per cubic centimeter, and that's about between water or ice and rock. And so we think it's made of a mix of water and rock because we have nothing better to say. That's a pretty good assumption. They seem to be pretty common planet-forming materials. Now, Pluto is a little bit denser, 1.8 grams per cubic centimeters, but it's about the same, essentially. So Pluto and Charon are not alone. You've heard that there are 4 extra moons in the system. What's very interesting is that all moons, and Pluto and Charon, all orbit in the same plane. And so rather than, it's still not something about how this came to be. Rather than the moons just being captured by the system, it looks like the entire thing formed from the same disk, kind of like a mini solar system, right? And so as Brian showed, this is kind of the leading theory or hypothesis for the formation of the system. And to get this to work, you need to have 2 progenitors collide, and the progenitors are of size intermediate between Pluto and Charon. And so they have to strike pretty much at the right speed, the right angle, but it works. And so what happens is that Pluto tends to form from the material that was kind of inside, like the cores of these things, and Charon from the outer material, kind of the outer shell. Okay, and whatever is left in the debris forms the small moons. So what's interesting here is that, keep in mind, Pluto is a little bit denser than Charon, so it's a little bit more rock-rich. And that's telling us that if it formed from the materials that were inside these progenitors and towards the center, the progenitors must have been more rock-rich here and more ice-rich here. So in other words, they would probably be a little bit differentiated between rock and ice. Okay, but it's not to say that they had a rocky core and an icy shell like you'd expect for Europa, for example, because otherwise Charon would be completely icy, and it's not completely icy. It has some rock in it, right? Otherwise, you wouldn't get a density of 1.6. So we have to come up with a way of having the progenitors evolve to the point where they have partial differentiation between ice and rock, but still keep some rock on the outside. So that was one of the goals of this work. And we've been trying to understand how this differentiation process works. So presumably, all these objects kind of form from a homogeneous mixture of ice and rock that then separates. And the way to separate ice from rock is just to have kind of rock fall through the ice and sort it by density. But to get this to happen, you need the ice to soften sufficiently, or even to melt. This will usually happen at the center first, because the center is the most insulated place from the frigid surface, right? And the reason why the interior warms usually in tight planets is because you have rheogenic elements that decay, and the decay reaction produces heat. And so this is what heats up most planets, especially these guys who don't have tidal heating, like Europa or Enceladus or other moons. So the center will get hot first, the rock will separate from ice, and this will proceed outwards. So you can get to intermediate situations like this, where you have a crust of undifferentiated material that's too frigid to kind of separate rock from ice. Or you can go all the way. Okay, so perhaps the progenitors kind of stopped here in this partial state, and then Pluto formed from this stuff, and Sharon formed from the crust and the ice. There's one more layer of complication, and it has to do with what the rock looks like. It's pretty hard to tell what the rock could have been that the planets formed from, but the best example we have are the most primitive meteorites that we have in the solar system, least altered. And these are chondrites, and chondrites are made from these little chondrules, which are little spheres of about a millimeter in size. And they're suspended in this matrix of micron-sized grains. So it's a very particular grain size kind of solid, right? So you have big grains and small grains. And if you do the math, you find out that the big grains settle much faster in water or in ice than the small grains would. It's kind of like dumping a big boulder of rock that will go really fast, but if you have a little bit of silt, it'll take a long time to settle. And doing the math, we find that the chondrules can settle to form the core, but the matrix can stay suspended and mixed with the water and the ice and kind of make maybe a mud ocean or frozen mud. And so you can get, in addition to this axis here, you can get a second axis where you can have incomplete differentiation because some of the rock stays suspended in the ice. And if you have entirely matrix grains, potentially you never have differentiation. The stuff always stays kind of well mixed. And you can have any sort of intermediate cases as well. All right, so what does that tell us about the progenitors? So again, our goal is to get a progenitor that's partially differentiated. So this is a plot that shows the thermal evolution. So the temperatures inside a progenitor, okay, before Pluto and Charon form, before the collision happens. So from the formation until the time of collision, which we assume takes place about 100 million years after their formation. It doesn't really matter when. It's about a good indicative time. So this is the temperature scale here in Kelvin. And the temperatures go from the center here to the surface. They're about 1,000 kilometers in size. And so what's happening here is that they form pretty cold. So you're way off to the left of the scale here. And then because of this radioactive decay, they heat up inside. And at some point, they reach a temperature threshold. And here, the threshold is the melting point of a water-ammonia mixture. And we assume that they have water and ammonia in them. And because of melting, the rock starts falling through the water-ammonia ice and form a core. We assume some fraction stays in fine suspended, and the differentiation doesn't take place all the way. There is a crust that remains. But with this particular model and others, it's not very sensitive to different conditions. You pretty easily get progenitors that at the time of collision are partially differentiated. So we can this way reproduce the densities of Pluto and Charon. All right, so that was one goal. The second goal is to find out what happens inside Charon afterwards, during its history. So when the collision happens, everything is kind of reshuffled, right? Charon forms from the outermost material, but during the collision, the material gets pulverized and reaccreted homogeneously. And so we assume Charon forms homogeneous again, but with a little less rock than Pluto. And so again, it heats up until it differentiates into a core and a muddy mantle. But now over time, the heat builds up in the interior because the heat from the radioactive decay doesn't get transported outward this fast. And so the temperatures reach the melting point for the ice. And so you have an ocean that lasts about 2 billion years. And it's quite a large ocean, maybe 200 kilometers in thickness in this model. But again, the model is quite robust here in terms of varying parameters and so on. And then it freezes. So the reason why it freezes is that at some point, radioactive decay just can't compete with transport processes. So when you have an ocean here, heat gets transported by convection instead of just conduction in the ice. And so Charon cools a lot faster. So eventually the ocean freezes. Once it freezes, again, the heat transfer becomes more sluggish. And so heat still builds up a little bit enough to remelt part of the ocean. It's a little colder and smaller than before, but we have this sort of secondary ocean here. I don't know if this is real or not. But the bottom line is that we can have oceans for several billion years inside Charon. That's the takeaway. OK, so this is all models. Do we have any evidence that this could be the case? And unfortunately, I knew this was going to happen because I had the keynote and I forgot to put away the the animations. OK, let me show you this. So on Sharon, remember there's this canyon here at the surface that was shown in the Warmth talk. And to me, this canyon is reminiscent of a baguette. As a Frenchman, I always think of bread. but the analogy is actually quite good because you get this when the baguette rises or swells when you bake it, right? And so on Sharon, you get this little canyon here because it looks like it expanded upon freezing, right? Ice takes more space than water, and so if you freeze an ocean, you would expect Sharon to kind of increase in size from freezing. And so perhaps this giant system of canyon belts at Sharon's equator is a sign that it would have formed upon freezing of the ocean. We can talk about dates later. Brian mentioned that most of the surface looks older than 4 billion years, so they would put it here. And I'm saying it happens here at 2 billion years. So there is an issue that needs to be resolved here. I would say I'm right, but who knows? OK, and then the second interesting thing you can kind of see here on the limb, and if you zoom in, it looks like this. There is this very interesting mountain in the moat that you guys might have heard from the press release from the New Horizons team. And this has been a puzzle. We don't see this anywhere else in the solar system, or maybe almost nowhere else. The closest analog that my advisor Steve and I could think of is the Hawaiian Islands. You can see here there's a little depression. It's a little deeper here around the island. And the reason why that is because when you have volcanism, so the new rock gets formed, and there's a whole volcano here, and it kind of weighs on the crust and kind of flexes it down. And so you can see the flexure here. So it kind of looks like this. So could this be happening on Sharon? Again, if you do the math, you can find the minimum, or the maximum thickness of the crust here, so that it'll flex. If it's paper thin, of course it'll flex. But if it's 100 kilometers thick, maybe it won't, right? And so you find out that if it's above a few kilometers, it's really hard to flex it this way. And the only way you can get something solid or not viscous for a few kilometers is that you need to have a lot of heat coming under it because the surface is so cold here. And the only way to get so much heat is to have some sort of cryomagma chamber, so some sort of viscous ice or maybe liquid right under the surface that maybe erupts a little bit of material and flexes the crust, or it just kind of comes under the crust and then it collapses over it in this sort of pit here. So again, I'm not saying this is happening today or that this has happened all over the history of Sharon, but perhaps when the last bit of the ocean froze, in the interior, the ice kind of took more space than water and kind of squeezed whatever pockets of water were left up to the surface. So Brad, you were asking a question about this there. How can you get this? By squeezing water, it's kind of a way of shooting it up to the surface and kind of overcoming the negative buoyancy of liquid water and ice. So anyway, just to sum up, so Sharon and Pluto likely formed when two partially differentiated progenitors collided, and we can reproduce the structure that matches the densities of Pluto and Sharon. The thermal modeling strongly suggests that Sharon had an ocean for a long time, not until today, but for several billions of years. So other solar systems are younger than ours, and it's very possible that there are oceans in many places elsewhere, even though not on Sharon today. And it looks like ocean freezing shaped the surface so that Sharon actually had an ocean at some point. Thank you very much.
Questions for Marc?
Hey, good talk, Marc. I just had a question. I'm not really a geologist, but for like the Hawaiian Island analogy, those are thought to be formed by like mantle plumes, which are different from like getting a volcano forming from a magma chamber. So I don't know. Is it just a issue of the size scale of the feature itself?
Yeah, I would say so. So when you talk about mantle plumes versus volcanoes arising from tectonic processes, and someone who's more of a geologist than me can correct me if I'm wrong. But essentially, it's just telling you that the magma has a deep source and kind of very local source. So that's the case for the Hawaiian Islands. The magma chamber here, you're talking about a very small scale thing compared to the scale of the plumes, where the plumes would be. and who knows if there are plumes, but the source of the magma is hundreds of, maybe thousands of kilometers deep. But the magma chamber here, you're talking just a few kilometers, right? So it's just a little blip around the plume, and maybe the ascent is kind of stalled because, again, the water is supposed to sink in ice. So it's competition between the squeezing forces that and the pressurization that makes the fluid go up, and the gravity that makes it go down. And so at some point, you might reach some zone of neutral buoyancy where you have a little bit of accumulation. I think that's what happens under terrestrial volcanoes as well. So yeah, it's not incompatible. Yeah. Yes.
So how is the surface age determined? Because generally I think about surface age as being determined in terms of crater counting, but that surface to me does not look saturated with craters.
Yeah.
So I was just wondering how they determine the surface age.
Yeah, that's an excellent question, and again, people more aware than me can answer too. So in the Kuiper Belt, it's pretty hard, right? The absolute dating we get usually from crater counting comes from the Earth to the Moon. So you can date radiogenically some rocks from the Moon. You know how many craters are on them, and so you have some sort of a scale. It's actually really hard to extrapolate the scale elsewhere in the solar system, and particularly in the Kuiper Belt, where the collisional history must have been so different. So the way it's been done is kind of with models of how the Kuiper Belt population changed over time through collisions and so on. And it's informed by the size distribution of Kuiper Belt objects currently as they're observed. So on the big end of it, the ones that you can see. And on the small end of it, mostly it's built from what we're seeing on Pluto and Charon. So it's kind of like a snake that bites its tail, right? You date Pluto and Charon based on what you see on them. And there have been competing models. Currently, the New Horizons team has strongly converged on a single model that seems very plausible. And according to this model, the surface of Charon is pretty old, even though it's sparsely cratered, just because it hasn't been impacted that much. There weren't that many impactors. So that's one model that everyone's agreeing on, but who knows, right? It's all model dependent. Our results of a late ocean saying that the surface is maybe perhaps, or at least the plains are 2 billion years old instead of 4 is also model dependent. So it's kind of reaching an agreement there, yeah.
We have one more quick question.
So assuming New Horizons data 4 billion years is correct,
Mm-hmm.
does what you found, does that contradict New Horizons? If there's an ocean underneath for 2 billion until 2 billion years ago,
Yeah.
does it necessarily have to show itself through surface features?
Not necessarily. You can kind of compute how much Charon should have swollen, based on how much ocean there was. So there was an ocean 200 kilometers deep, and the density of water is blah, and the density of ice is blah, then Charon should inflate by blah. And essentially, you can kind of account for the whole extension through the canyons, for example. But the canyons themselves look like they're 4 billion years old. So in this sense, it's contradictory, but perhaps the canyons are due to something else, and there could have been an ocean that was never expressed. Yeah, I don't know.
Okay, we're going to move on.